So what I will talk about is the perspective we have from modeling and how the modeling community really needs observations, not just from remote sensing, but any type of observations. And I'll do that from the perspective of small scales, because in the last 2 decades, numerical oceanography has come a long way from really sort of idealized simulations to things that begin to look very realistic. And a lot of that is just a result of resolution. And so what I will start showing is basically a sequence of nested computer simulations. And so at the large scale, this is all done using ROMS, which strictly speaking stands for a regional ocean modeling system, but regional is a relative concept. So at this large scale, the ocean looks as we've known it to be. It's geostrophic. There's geostrophic eddies that are large scale, move relatively slow, and are very much linked to the shape of the sea surface. And so what we often use to visualize this, because it's an important dynamical quantity, is the surface relative vorticity. And so what you see here in this image is both sides of the Gulf Stream in positive and negative surface relative vorticity and the Gulf Stream rings. And so this is still considered geostrophic, which means that the local Rossby number, which is the normalized vorticity, is less than order 1. And what we'll see is that as we go down in resolution, you'll see different things appear. So this is a nested simulation, and if you could freeze this in your mind, what you see is this very clear seasonal cycle, which has to do with the depth of the mixed layer. Depth of the mixed layer provides the energy that drives the submesoscale. But also what you start to see asymmetries between positive and negative vorticity. And it has to do with vortex stretching over fronts and eddies, where we see surface convergence, and as a result of that we see positive surface vorticity. And so this is a very non-geostrophic phenomenon. And let's go down a little bit, increase the nesting. So we keep zooming in. So what you should notice is this organization of the submesoscale along fronts. So you see these structures, these filamentary structures, they're fronts in density, and those fronts become subsequently unstable to mixed layer instabilities, and you see this increasing asymmetry between positive and negative vorticity. And so this is a prediction that these models make. See, I went down one more. We focus on this topography interaction, and I'll skip you the remainder 2 version of this, where we go down to horizontal resolution of 10 meters. This plot really summarizes the transition between geostrophic balance at large scale and ageostrophic effects at smaller scales. And what I want to emphasize, what we're looking at here, is not just waves and geostrophic balance motions, because these simulations are designed to have very little wave activity. The surface forcing is low frequency only, we have no tides. So the directly forced internal wave field is low in energy. But still what you see is that in this graph you see the ratio between the divergent and the rotational part of the surface velocity field. And so for this we use the rotational part as a proxy for geostrophic flow. And what you see is that for large scales, it's all rotational. It's all geostrophic. But as you go to, in this case, roughly 30 kilometers in wavelength, the divergent part of the flow starts to become increasingly important. And so what this indicates, and actually the one on the right is more directly, there we've just taken the sea surface height field and just assumed that all of it predicted the geostrophic flow. And what you see there is that in that case, the geostrophic flow really sort of blows out of proportion with the total flow. And it's because a lot of it isn't actually geostrophic. And so this shows that geostrophic approximation is, it's good and well, but it's valid only up to sort of wavelengths of 30 kilometers at mid-latitudes. But we've done more than that. Models have come a far way, and in addition to just saying, oh, geostrophy isn't valid at these small scales, we've made a lot of progress in knowing what actually is going on at those scales. And so these are just a number of plots to illustrate some of the aspects. What on the upper left, you see the gradient of buoyancy. So it really just indicates where fronts are. The one on the right is similar gradients for velocity. And then on the lower left, we have the vorticity. Lower right, we have the divergence. And so what this shows is that these structures really do correspond to buoyancy gradients. So these are all frontal or small-scale eddy structures. And what you see is that there's a strong correlation between positive surface relative vorticity values and negative divergence. So these are areas where surface convergence occurs, and we have, because the water has to go somewhere, we have vertical velocities there. And those fronts are characterized by cyclonic regions of vorticity. And so this talk is way too small to talk about everything we know of the submesoscale, but I've named a couple of things. So sure, we see departures from geostrophy. We see the emergence of submesoscale phenomena, and several other people have shown that. And the emergence really linked strongly to the amount of available potential energy. And the amount of available potential energy is a result of horizontal buoyancy gradients and a deeper mixed layer. So that's why in the summertime, when the mixed layer is very shallow, you see much less submesoscale energy. And in the winter, when the mixed layer is deep, you see a lot. There's a very strong asymmetry between cyclonic and anticyclonic vorticity, with significant tails on the positive vorticity end. There's significant surface convergence. So unlike the geostrophic flow field, which really has strictly no vertical velocity at all of any amplitude, submesoscale starts to have order 1 vertical velocities. And then sort of the more recent process is in what then drives the dynamics at these small scales. We find that frontogenesis, so the growth in amplitude of the front, amplitude is really the amplitude of the gradients, which result from a decreasing length scale. So the older existing thoughts were that happens as a result of external straining and resulting secondary circulation. But we find a strong role of what we call turbulent thermal wind, where there's an interaction between the mixed layer turbulence and horizontal buoyancy gradients. And even more recently, we find that once you have order 1 divergence, the divergence evolves itself, and you don't need anything else. But once you have divergence, the evolution of the front is very well predicted by the fact that there is divergence. And so, in summary of that, things happen at small scales. And the older paradigm really was that we have geostrophy in the ocean, and we have waves, and they mostly peacefully coexist, and there's some interaction, but the focus was on that geostrophic field, and then we parameterized the effect of waves. And we learn more and more that there's important dynamics happening at these submesoscales. Some big remaining questions is that models do relatively poorly on the coupled atmosphere-wave-ocean interface. And so this is where satellite observations like what we're discussing today are important. Scatterometers give us information. Models don't have that full 3-way interaction well represented. And there's some parameterizations, but a parameterization is really just that. We don't know what sets the limits to fronts. So we know how they become sharper and sharper. We don't actually know what limits that. In models, the limits of frontal sharpness are the result of a finite resolution. Reality is different, and we don't really know what limits that in reality. And we keep finding that fronts are sharper in reality than we originally thought, and hence the remark by Bertrand this morning about 40F. Well, 40F is really nothing, it could be anything. The big question is that many speakers have spoken about vertical velocity. Vertical velocity is nice, but vertical velocity by itself doesn't tell you the vertical flux of material. Right? So in order to get a vertical flux, you need to have a correlation between density or tracer anomalies and vertical velocities. And so that's a good thing too, because at least in the models, the spectrum of vertical velocity is mostly white. So as we increase horizontal resolution, the scales of vertical velocity keep increasing. But the vertical flux doesn't necessarily do the same. And that's because it needs to correlate with the shape of the tracer variance. And then a hot topic is the interaction of the submesoscales and internal wave field. And we think that the interaction between these two processes are particularly important because their timescales overlap. So the geostrophic field is slow and the waves are fast, and so waves can provide dissipation. But timescales of submesoscale and waves, they overlap, and so there's a lot of mutual energy exchange possible. I wish I had the time. Models is just a model, so we need observations. I'm going to go a little faster. So in the last few years, we did a bunch of massive drifter release experiments. And the map on the right is just all tracks on top of each other. These experiments involve hundreds, and in one case even 1,000 drifters. So once you start putting in drifters of that scale, you can start to resolve these submesoscale things. And in this particular case, you can see how the drifters tend to accumulate on lines, and then those two lines start to collapse on a single point. So they show that the predictions of the model of significant surface convergence are in fact realistic. These experiments included other platforms, airplanes with infrared SST, radiance contrast. Ernesto already showed these plots this morning. And now we have the drifters to validate some of these remote sensing. So the drifters in this case give a quantitative match to, in this case, the Doppler scat stuff. A big scientific discovery of this is that when you put stuff in the ocean, it doesn't just spread. I mean, this is sort of the classical view where you put a patch of dye in the ocean and it disperses. In the case of surface particles, like drifters or oil, what we find is that, sure, there's dispersions. This is a pairwise separation. And this is a PDF, probability density function. So some of those pairwise separation keep increasing over time. But there's also lots of drifters that instead of spreading, they tend to accumulate together. And so that's the result of these frontal processes, which leads to, for instance, if you have an oil spill, that oil tends to accumulate in lines. And so that's not an oil property, but that's a result of the dynamics in the surface layer. And understanding that better is important. So what those drifters allow us to do, these large drifters, you can do triangle analysis. And so what you find with these drifters, you find statistics that correspond to the statistics of the model. And you can do dual divergence vorticity. You see this asymmetry with a tail in high positive vorticity and negative divergence. And as a last example, when I said that result how divergence evolves itself, you can actually verify that with actual drifters. We find a very good match between that theory and how real drifters evolve in the ocean. Of course, drifters are limited in their approach in the sense that it costs a lot of money to deploy them, and eventually they die. And so sort of they're limited in space and time. You cannot cover the whole ocean, even though Argus is doing a good attempt. At these scales, you cannot do that. The second one is that they sample the ocean very anisotropically, because drifters tend to go where the convergence is negative, and so they tend to collect in lines. Scatterometer, on the other hand, provides spatially unbiased and much better coverage, but of course it doesn't have the temporal resolution of these drifters. So at the summary, so point I wanted to make is that models are actually have been driving the small scale field for a while. They're making predictions and they're running to a certain degree ahead of any observations. There's a lot of understanding about what the dynamics are at those scales. However, models are still parameterizing important parts of the physics. And so the biggest things that come to mind is they parameterize the turbulence in the boundary layers, and they parameterize important parts of the exchange between atmosphere and ocean. And so, for instance, they don't explicitly take into account the non-local role of surface waves as the surface waves interact with fronts, then modify the roughness of the ocean surface, which in turn would modify the wind stress, which in turn has the ability to modify the frontal convergence. And so, this last point, I thought it was so important that I made it in color, and then I made an extra slide of it. And that's just because this conference is much about observations and how observations provide data that the oceanographic science community would be happy with. And so I am an oceanographic scientist, and so I can see two very distinct roles for observations. And so one of the roles is to do process studies to help advance models and to validate models where they exist. And so that's a very particular application where you, depending on the process that you're thinking of, you need to think carefully about what type of observation. And so in the context of satellites, this is where you could argue, for instance, okay, I need super high resolution, but I don't need it over the whole globe. I would be super happy if I could just get it over a small area. And in that sense, I would love to get it as high frequency as possible. In that sense, what you should aim for is not necessarily to have a one-to-one match between the model and the observation, but you want to look for statistical truths. You want to look at the statistics of surface kinematics. You want to get a something that's true for dynamics, even though the realization per se may be different. And then we have the second application, which is very, very different. So this is for data assimilation processes. So currently, ocean data assimilation, ocean forecasting, is heavily limited by the availability of data. So what ocean forecasting does well, it forecasts the slow, large scales. And it's because, and I forget who said it this morning, they rely heavily on satellite altimetry. And so ocean models do reasonably well, but at those scales and at those time scales. What they do terribly at, not necessarily in terms of physics, but in particular realization, is the smaller scales. And they do terrible because they cannot be constrained because there's no data. And so for that, you need very regular, very spatial everywhere. What? I'm speaking now. You can talk in a minute. What I would want if I had a product.
Sincerely, it's only my opinion.
Yeah, but why don't you give me 30 more seconds and I'll let you speak.
Yeah. I don't approach it. Okay, sincerely.
That's fine. Then, as soon as I'm done, you can speak up. So what I would need if I had an ocean product where, for instance, the rescue services or oil spill prediction, I would need regular data to assimilate into that model. And I would need, if I need that prediction at small scales, I would need the data at small scales. And so it'd be nice if somebody gives me high resolution data from last week, but the predictability of those small scales doesn't last for a full week. If I need small scales, I need the data this morning, and it will have a time scale of predictability maybe up to a day. After that, the correlation between the observation and the actual state is finished. And with that, thank you. And then we'll let Bertrand play.
Okay, so there may be other questions also, and I just want to point out that Sophie Kravat was telling that at the equator, we're talking about 400 kilometers, 40 days, so there's a lot of room for improvement at the equator.
Right.
No, it's just a general comment on the data assimilation. I mean, I mentioned this morning, one of the things we need to actually get over is the fact that we're never going to have data or a PI if we're not careful. Can you just control yourself? We need you for it. I mean, you know, this is a problem. We're never going to have all the data we need, and the whole purpose of using models from time immemorial is that we can assimilate snapshots. So regularity in space and time is there, but in theory we should be able to get our models constrained sufficiently well, numerically and with observations, to actually allow us to maximize the use of these snapshot data that appear in a non-regular manner. And we need to learn how to do that, because ultimately that's what we're going to get from many, many missions in the future. So I take your point that in an ideal world it's perfect and you get the best result with regularity in space and time, but we need to get over that. We need to move on. This is like, that's the girlfriend you want, this is the beer you want, but you can't have that one, so we're going to go to the other one.
Okay, so I'm sorry if I stress the word regular too much, but so regularity is not necessarily important, but it should be known that all these solutions are chaotic, and they have certain Lyapunov exponents, and so there's a limit to predictability. And so sure, if you give me a snapshot now, I'll put it in, and it'll be good. But
For 1 or 2 hours. Yeah, exactly.
Or for a day. So so the point I was trying to make is not that I don't care about whether it's regular, but it has to be here if you want me to predict something for today. And if you give me something from last month at the small scales, it just doesn't add much in terms of the predictability. Regularity, I'm sorry I used the word, regularity is irrelevant in this. It can be scattered all over time and space. But the point is that what we currently have is the only data that regularly that often occurs over the ocean is satellite altimetry, and so that is by itself it's a limitation because it doesn't provide enough information on the smaller scales, which means we can constrain the smaller scales.
Or in space.
I think
In space.
we can
Yes,
follow that
actually,
discussion later for discussion. And I really emphasize these 2 points. The first one, we shouldn't forget about the first one.
Right. So the first one is super important. It's just, I don't know, I was thinking about it, and for me I see a big distinction. And so the fact that it's not, that it's sort of ad hoc and one time only makes data still super useful because you can do process studies.